Okay, hello and welcome to part 4, the final part of the Practical Geochemistry Data Analysis PGDA exam feedback for question 4 of 2019. So just cracking on again, the overall mark distribution, very good. Many people did very well, some people less so. And looking at question 4, one of the best questions that was answered, as in best answered, maybe not the best question, but the best answered question of the exam. So well done there. And let's have a little look at what that was asking. So yeah, again, people did well. Good job. So this was a question about boron isotopes specifically, but more generally, kind of the things we need to consider when using isotope proxies in kind of environmental samples. So there was this horrific equation in the question. You didn't really need to know all of the details of this. So that the first part of the question really is asking you, out of all of this horrendous thing in the let's give myself a lovely pointer. Lovely, this horrendous equation here. Really, out of this equation, what does this alpha and what does this delta thing mean? This is really the bulk of what we're looking for. So in the more generic sense, alpha is the fractionation factor. So you've got some marks for saying that. You could have said that it's the ratio of the absolute isotope ratio of between two phases, but really specifically in the case of this example, it's the fractionation between the two phases dissolved in water, so between boric acid and the borate ion. So it's the heavy isotope divided by the light isotope, boron 11 divided by boron 10. So you could have gone to a little bit more detail rather than just saying it's the fractionation factor. Similarly for the lowercase delta 11b, so that's the measured isotope ratio of boron in a sample compared to some arbitrary standard. So that's this thing over here. You could have given the equation for that. You could have mentioned that the standard is completely arbitrary. It doesn't really matter what it is, as long as everyone uses the same one. It's all good. So those are the kind of things we were looking for part A. Fairly straightforward. I think most people got a whole bunch of marks for part A, which is pretty good. Okay, so part B. Again, this is a question that is, I guess it's asking you to do one thing and giving you some instructions to do that. Okay, so it's really asking, why is the isotope ratio of borate ion kind of dependent on pH? Now, you could split this into a number of different parts. Why is it different to the boron isotope ratio in the boric acid? Why is it different to the boron isotope ratio of the total boron in the ocean? And also, your answer must include some diagrams. If you didn't include diagrams, then you're not doing what the question asked. So make sure you do follow the instructions in questions. Some people lost a few marks for not doing that. So this is what we're really looking for in terms of answering the question. So I guess first of all, we're going to take a little bit of a sidestep into the boron chemistry. So the first thing to note is that there are two different species of boron in the ocean. There's boric acid and there's borate ion. There is an equilibrium exchange between those two. Okay, and that can be reflected by an equilibrium constant, if you must. But importantly, that equilibrium constant is dependent on the hydrogen ion concentration. So the position of this equilibrium between these different phases is dependent on how much concentration of hydrogen ions in the solution. So it is dependent on pH. So a good diagram to draw to show that would be this one here showing for different pHs the different concentrations of the two boron species. So at low pH over here, we've got predominantly boric acid, and at high pH, we've got predominantly the borate ion. Okay, so the next step in the reasoning as to why the isotope ratio of the borate ion is dependent on pH is that there is an isotope fractionation between the two species. So there's some fractionation factor alpha between the boric acid and the borate ion. Now you could go into a little bit of detail to say why that is. Like maybe one phase has got a different bonding environment, therefore favours the heavier isotopes over the lighter isotopes. That would be worthwhile doing. But the important thing is that the isotopes are different between these two things. Now that fractionation factor is not dependent on pH, but importantly, if we look at the kind of the mass balance of boron isotopes, if we were to take all of the boron 11 in the boric acid and in the borate ion, we were going to add that all up. That should equal the total amount of boron 11 in the ocean. You do the same for the boron 10. So you could do an isotope mass balance in the same way that we did for strontium isotopes in the practical, where we look at the isotope ratio of the total amount of boron in the ocean times the total amount of boron in the ocean. That must equal the sum of the isotope ratios and the amounts of the different species. Okay. So the important thing here to note is that if we then change the proportions of the different boron-bearing species, so if we change the proportions of boric acid and borate ion because we're changing pH, if we are going to maintain a constant fractionation between them, and we're going to maintain that the total boron isotope ratio has to be the same, we're not taking isotopes in or out of the ocean, then that means that the isotope composition of the two components must change. So at very low pH, if all of the boron is as boric acid, then the boric acid has to have the same isotope composition as the total borate pool. Whereas at really high pH, if all of the boron is as the borate ion has to have the same isotopic composition as the bulk. Okay, so this explains why the boron isotope ratio of the individual components must change as a function of pH. So that's something that I think quite a lot of people explained quite well, used the kind of sensible diagrams to explain that. A few missing out on some of these subtleties of these things having to be true for this to be true. So there we go. The next part of the question looks into not the dissolved boron in the ocean, but into how this stuff actually gets incorporated into calcium carbonate. So the question says that boron can be incorporated into calcite only from the dissolved borate ion rather than from boric acid. This has been led to the use of boron isotopes at marine calcite as a proxy for past ocean pH. Okay, so that's a statement that has happened. So the question is, so we've basically established already that this borate ion isotopic composition that will change as the ocean pH changes. And then the question is asking, why would the isotope ratios of boron in marine calcite be different to that from the boron in the ocean which they form from? Now I've said boric acid, this was an error. It should of course be borate ion, but I didn't look through all the answers. Nobody either spotted this mistake or you ignored it and used the borate ion as a correct, corrected it anyway. So no one was really disadvantaged from that little minor error. So what we're looking at here is we have shown that the this boron isotope composition of the borate ion, that is a function of the ocean pH. Now what the question is asking really is why this isotope ratio, so if we're taking boron from the bulk ocean, we're fractionating it into one of the the boron species in the ocean, in this case the borate ion, and then some of that boron gets incorporated into calcium carbonate. What we're really asking is, why would this isotope ratio be different from this isotope ratio? What the question is not asking is about these processes. Why is the boron isotope ratio in the calcium carbonate, why is that different from the whole ocean? Okay, what might cause some of these other things which might affect the boron isotopes in the borate ion to change? It's really looking at this last step here. Okay. So what we're really looking for is there being some kind of fractionation factor between the two boron-bearing species here, in this case the borate ion and the boron bound in carbonate, and an assumption that fractionation is in isotope equilibrium, which it is of course not. So you could have gone into discussing isotopic equilibrium, what we do about that, whatnot. And that's really what the last part of this is about. It's about there are differences between boron isotopes in the dissolved borate ion and in the calcite. And when we're using those measurements of boron in the calcite, what do we need to do? What do we need to consider when trying to convert them back into the boron isotopes of the borate ion and therefore using it as a pH proxy? So what I was really looking for here is the kind of stuff we talked about in the lecture in terms of having to do empirical calibrations, having to do temperature corrections, because fractionation factors might be temperature dependent, and they are temperature dependent. We need to worry about that, and what we can do about that. So I think quite a lot of people mentioned some sensible things in that. That was really good, talking about there being a salinity correction or salinity dependency on the fractionation factor and also on the pKb, because we need to ultimately convert these into a pH. So we need to know the equilibrium constant for the speciation of boron. And saying not just that we have to do these corrections and they are pressure, temperature, and salinity dependent, but by saying also that actually some of these corrections don't matter. For instance, if we're doing a pressure correction, if we measure planktic forams, the pressures are all going to be the same, so we can ignore that. Yeah, and what kind of proxies we might want to use for temperature corrections in forams as well. So giving some more detailed of examples of how we might do this, rather than just saying, oh, we need to correct for temperature. What kind of proxy we're going to use for temperature, what might we measure that in, that would be good things to do. So again, a good set of answers, mostly for this question. So yeah, well done for getting this far in the whole video fiasco thing. And well done if you were one of the green people, because really well answered. So yeah, I am going to stop that there, and yeah, stop that there. Oh, there we go.